Good day, I'm Norman Wappeger. In today's video, we want to introduce the Hindu Arabic numerals as a way of extending our understanding of natural numbers. So for us, the Hindu Arabic framework is not just a shortcut for efficiently describing natural numbers. It's actually a way of extending the arithmetic of our primitive natural numbers into territory that's beyond what they themselves can support. Okay, so the setup is this, that we're starting with this vexil point of view. So a vexil is an M set of singletons with type vex. And then last time we talked about base 2 vexils. These are vexils together with an additional exchange rule. The exchange rule is such that if you have a pair of singletons n in a multiset, then you are allowed to exchange them for a single singleton of n plus 1. And conversely, a single n plus 1 singleton can be exchanged or converted to these pair of n singletons. Now here n is a natural number, a primitive natural number, which we assume we've already established. Those were our M sets of our underlying strokes or marks. So today we want to do a very similar kind of thing, but we want to move from base 2 to the more familiar base 10. But what we're going to be basically doing is very analogous to the base 2 story. So the definition is that a base 10 vexil is a vexil, so something like this, coming from the original vex, together with the following exchange rules. So the exchange rules now are of a more complicated type because there's 10 things on the left-hand side rather than 2 things. So if we have a singleton n with another singleton n and another 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 and another, all in an M set, then we're going to agree that we can take those 10 singleton n's and replace them with a single singleton n plus 1. And conversely, one of these can be exchanged for these. And the crucial thing, of course, is that there are 10 here on the left-hand side. That's why we're getting a base 10 vexil. And so our type for these base 10 vexils is vex 10. And we're going to agree that this particular type of vexil will have an alternate name for its type, just num. So we're actually going back to the notation that we started this series off a long time ago. We had num, but now we're introducing it in a somewhat different way. So now num really does represent a Hindu Arabic numeral. We'll refer to them as Hindu Arabic numerals. And they are officially somewhat different objects from natural numbers, although in practice we will consider them to be natural numbers, just sort of a familiar alternate form for natural numbers. But officially they are something a little bit different. They're built up from natural numbers, but you can think of them as more complicated, sophisticated entities with a more sophisticated arithmetic that allows one to extend arithmetic to higher realms. And the addition and multiplication of these base 10 vexils is really the same as for vexils. All right, so let's have a look at an example. So here's a vexil, 0, 0, 1, 1, 1, 3, 4, 4. Now in this world of vex 10, so we're assuming we're in vex 10, then this thing here can be represented in our usual kind of vexil notation by giving a column vector kind of approach. There's 2 zeros, there's 3 1s, a single 3, and 2 4s. So our vexil n is represented by this vector. Now using the exchange rules in vex 10, this 3, for example, one of them could be exchanged for 10 of the previous ones. So if we change this 3 to a 2, we can compensate for that by adding 10 to the 2. So it becomes 12. So this vexil is the same as this vexil in vex 10. Another thing that we could do is, starting with this, we could replace this one of these things here with essentially 10 of the previous. So we take one of these 4s and replace it with 10 3s, giving us altogether 11 3s and only 1 4. Another thing that we could do, starting again with this, is to take these three ones and convert them all into zeros. So each one of them would be converted to 10 zero singletons. So the three altogether would give us 30 to join with these ones, giving 32 zeros. So this is also equal to this. And if we convert everything into just zeros, because we can do that, we can convert each one of these fours to 10 threes. We can convert then the threes to 10 twos, the twos to 10 ones, and the ones to 10 zeros. It's like converting everything into $1 bills. You convert your $1 bills, $10 bills, $100 bills, $1,000 bills. You convert everything into just $1 bills. This is what we're doing here when we get that this thing is the same vexil as this one. So it's 2132. 2132. So in vexil 10, these are all legitimate and equal expressions for this original vexil here. We have a flexibility in this system. It's a very useful kind of flexibility. All right, so let's have a look at some bigger numbers in this light. So we're still working in our base 10 vexil framework. And let's look at this one, which we'll call n. And it's an m set of singletons. And we'll suppose that there are actually 47 of these zero singletons. 2 singletons of 2 and 15 singletons of 3. And let's consider also another one called m, which has 3 singletons of 0, 4 singletons of 1, and 936 singleton 2s. Okay, so this n then can be written in the sort of standard vector form as 47, 0, because there are 0, 1 singletons, 2, 15. So this vector of multiplicities captures the m set. It's like a list that captures the multiplicities in the underlying m set. Okay, we can rewrite this thing because this 47 here can be converted into 7 zeros and 4 ones. Okay, so we can take 40 of these zeros, which are strung out here, and convert them into 4 1 singletons, and so we can do that. And similarly, the 15 here, this represents 15 threes, so we can take 10 of those and convert them into a single 4, giving us then 5 threes left over and 1 4. And something else that we could do is convert everything into zeros. So the 4 here could be moved there, would give us 40. The 2 could be moved there, giving us essentially 200. The 5 could be moved there, giving us 5,000. And the 1 could be moved there, giving us 10,000, with the result of the number that we usually call 15,247. That's kind of a compressed view of this base 10 vexil. This is the expanded view. This is the view that's more familiar in terms of base 10 number, where each one of these entries is a digit from 0 to 9. Okay, and here is m. This vexil here is 3, 4, and 936. And if we like, we could convert this 936 to 693. So basically, we'll take 930 of those singleton 2s and convert them into 93 singleton 3s. And we could go one step further, take 90 of those singleton 3s and convert them into 9 singleton 4s. Now this thing is in extended form. And here's the corresponding compressed form, where we bring everything to the top. So this 4 becomes 40, this 6 becomes 600, this 3 becomes 3,000, and this 9 becomes 90,000, for a total of 93,643. All right, so let's look at addition first. So we're working in our base 10 vexils, and we have our vexils n and m. Here they are here in our usual form, and we want to add them. Okay, so here's the usual story that we're all familiar with. So to add these two numbers in Hindu-Arabic form, we would write one on top of the other like this, line up the ones, the tens, and the hundreds, and so on. And then we would start adding on the left. So 7 plus 3 is 10. We write down the 0 and carry the 1. 4 plus 4 plus 1 is 9. 2 plus 6 is 8. 5 plus 3 is 8. And the 1 plus 9 is 10. Write down the 0, carry the 1, and then write down that 1. Okay, let's look at the same operation in a vexil point of view. All right. So this number n is represented by this vexil. Basically, the left point here corresponds to the bottom entry. So 1, 5, 2, 4, 7. Or another way to think about it was we're reading it from the ones first. 7, 4, 2, 5, 1. And this one over here is 3, 4, 6, 3, 9. So to add them in the vexil world, we just add component-wise. 7 plus 3 is 10. 4 plus 4 is 8. 2 plus 6 equals 8. 5 plus 3 equals 8. 1 plus 9 equals 10. We don't mind that maybe some of these entries are bigger than 10. This is allowed in this base 10 vexil system. This is also a legitimate base 10 vexil. But we can, if we want to, convert it into a extended kind of form. We can convert these 10 zeros to a single 1. So we have then 0 zeros and 9 ones. 8, 8, and this 10 here can again be converted into a 1 of the next kind, giving us 0 and 1. So when we read back up, 1, 0, 8, 8, 9, 0, we get the same thing as before. So the benefits of this approach, they're obviously quite similar in this situation, but the benefits of this approach are more obvious with sums involving many numbers. So if we had to add not just 2 numbers, but we had to add maybe 10 or 100 or 1,000 numbers, then there would be a considerable advantage in working horizontally. For the reasons I've already talked about in our last video, that basically there's going to be more room in this horizontal form to have big numbers occurring here. We're not constrained by a relatively small area there to actually place a column total. We'll see this figuring in our discussion of multiplication next. All right, so let's have a look at multiplication, which is considerably more subtle. Let's multiply n times m. There's n, there's m. And here's the usual story. We write them down horizontally, and then to multiply them, what we do is we essentially multiply the first number by each of the digits of the second number, and then add totals. So we multiply 15,247 first by 3. We start on the right. 3 times 7 is 21. So we have a 1 and a 2. We carry a 2. And then 3 times 4 is 12. We have to add the carry of 2, giving us 14. So we write down the 4 and carry the 1. And now 3 times 2 is 6, and the 1 makes 7. Then 3 times 5 is 15. We write down the 5 and carry the 1. And 3 times 1 is 3, plus 1 is 4. Okay, and then at the next stage, we multiply by this 4, as you all know. But I know you all know this, but let me do it anyway. So the 4 then multiplied by these things is 4 times 7 is 28. So there's an 8 now. But because we're multiplying by this one here, we have to actually sort of start 1 over. So we put the 8 there and carry the 2. We put the 2 up here. 4 times 4 is 16 plus that 2. Actually, it's that 2 there. That's the second 2 that was a carry. The 4 times 4 is 16 plus the 2 is 18. So there's an 8 and then a carry of 1. And then 4 times 2 is 8 plus 1 is 9. And we carry on like this. The next one will, with multiplying by 6, will give us this. The next one, 3, is the same as that first one there, so we can copy that one there. And then when we multiply by 9, we have some more things to do. Now note that every time we do this, we are introducing more carries. And we want to record those carries, and you can see that the carrying kind of area gets a little bit full, right? Because every time we have a carry, we have to write it down someplace so that we remember at the next step to add it. And if we were going to do this by hand, we see that if we had two numbers that were maybe 100 digits long, then this area up here would get very crowded. It would be actually a little bit impractical to do it. We would get mixed up in terms of which one is the relevant carry, because there's so many carries up there. Okay, so anyway, we have these various single products, and then we have to add them all up, and we start from the right, 1, and then 4 plus 8 is 2, and there's another carrying going on there, and then we add up the columns and carrying in the usual fashion, and we end up getting that number there. Okay, so the carrying story really is, I guess, what makes this challenging for students. They have to learn how to do the carrying in the right way. And there's quite a lot of carries that are involved, especially if you have bigger numbers. And as I've said, it can get quite messy and maybe overly complicated if you have two very big numbers. Now, I wouldn't be surprised if many of you younger viewers regarded that previous kind of calculation with the multiplication as almost a dinosaur kind of activity. It's probably not something that you had lots of training in, because these days the calculator is never far from your fingertips. And so that whole procedure is maybe something that formally you are familiar with, but actually doing it practically might be a little bit of a challenge. And maybe some students have actually never really been taught this at all. Maybe in some places multiplication is just something that you do on a calculator. In that case, I think this Vexel way of doing things, which I'm now going to show you, provides an interesting alternative to the familiar one. One which I think is somehow conceptually easier to understand. It's easier to understand what's going on and why we're doing the various things that we're doing here in this approach where we're thinking about the numbers as being vertical rather than horizontal. So we're going to take the same two numbers and regard them in a Vexel fashion. We'll multiply them as columns. So 15247, 15247, 93643, 93643. And what we're going to do is very similar to what we did in that previous thing. So we're going to multiply this first column by 3. This is really just poly-number multiplication. Okay, but we're going to think about it as taking this and multiplying it by 3. And 3 times 7 is 21, 3 times 4 is 12, 3 times 2 is 6, 3 times 5 is 15, 3 times 1 is 3. Notice we're just writing down the various products that are obtained and not doing any kind of adjustment. We're just writing them down. Then when we move to the next digit here, the 4, we're going to do exactly the same. Just multiply this 4 with all of these, record all the possible products. 28, 16, 8, 20, and 4. And then we multiply by 6, and we get this column here. Each column is offset 1 down from the previous one. 6 times 7, 42, and so on. And then we multiply by 3, we get this column. And finally, multiplying by 9, we get 63, 36, 18, 45, and 9. Note that we haven't done any carrying. We're only concerned with multiplications between these various digits. And if you go back to the previous page, you'll see that each one of these multiplications was a multiplication that we did there as well. Just that we typically included it with a carry from the previous one. We didn't write it down explicitly, we only wrote down the rightmost digit. Here we're writing down all the possible products. Now what we have to do is just add all of these things up horizontally. 21, 12 plus 28 is 40, 6 plus 16 plus 42 equals 64, and we add horizontally all the way down to 9. This is an answer. This is what the product of these two things is in our Vex 10 framework. But it's not in the standard extended form. To put it in a standard extended form, we want each one of the digits to be between 0 and 9. That means we have to convert more than 10 things to one of the next one. So we take this 21 and we convert the 20 to 2 of the next type. So then we only have 1 of these, and now we have 42 of them. We write down the 2, and we take the 40 and convert them into 4 of the next type. So now we have 68 of these. We write down the 8 and convert the 60 into 6 of the next kind, giving us 74. We write down the 4 and then convert the 70 into 7, giving us 117. We write down the 7 and convert the 110 that's left over to 11 of these. 11 added to 76 is 87. We write down the 7 and add 8 to here, giving us 47. We write down the 7 and add 4 to here, giving us 52. We write down the 2 and add 5 to here, giving us 14. We write down the 4 and add 1 to here, and there's the 1. So the carrying is all concentrated in this last step as we convert each one of these into something that's just between 0 and 9 by converting the other ones using the exchange rules to fellows further down. And you can see we can do that in our heads reasonably efficiently. So this is a way for us to circumvent a lot of those carries that were sort of distributed throughout the whole procedure in the last case. Now all the carrying is sort of concentrated at the end. Mind you, there's also a little bit of carrying as we add up these rows here. So when we added up these rows, we would of course also have to do a little bit of carrying to add up to get to 110, typically. Okay, so I claim that for multiplying big numbers by hand, especially if someone is not too proficient and hasn't spent a lot of time practicing, this is a much more reliable and simple method. So this is multiplication using our Vexel approach, basically really the approach that goes back to polynumbers, our polynumber orientation, to do things horizontally, one column at a time, and to convert all the carryings at the end. And the number that we get is the same number that we got with the other method. So to summarize what we've done is we've introduced these Hindu-Arabic numerals, which we're denoting by type num, which you can think of as standing for numeral now, as essentially base 10 vexels. Okay, and these are built up from our primitive natural numbers. So we assume we already understand our primitive natural numbers, and these vexels as objects are m sets of singletons, where a singleton is a list of one natural number. The arithmetic with these numerals is defined independently of our arithmetic with primitive natural numbers. It's not that we're just taking the prior arithmetic of natural numbers and just converting it into an arithmetic for these things. We're defining a new arithmetic on these guys, which is extending the arithmetic of natural numbers. It applies to numerals which are so big that they don't refer to actually any particular primitive natural numbers that we can write down. So our arithmetic is capable of dealing with numbers that have hundreds or maybe thousands of digits long. These numbers would be too big to actually represent primitive natural numbers. But nevertheless, they have an independent arithmetic which we have just been defining here. And the whole thing really rests on the Vexel arithmetic, or the polynumber arithmetic, and these exchange rules that allow us to convert 10 of one level to 1 of the next level. There's something to be done here. One has to verify that the arithmetic is actually well defined, that this exchange condition of changing 10 of these with 1 of these is actually well defined in the sense that the arithmetic is still independent of which of the various possible forms of a vexel that we use. So if we have a vexel here and a vexel here, we multiply them, and then we change the two vexels by making various applications of the exchange rules. We want to then convince ourselves that what we get is exchangeable with what we originally got, again, by just the exchange rules. So that's a great exercise for you to think about. And we see that the arithmetic with these numerals, these Hindu Arabic numerals, is actually quite a lot more efficient than arithmetic with our primitive natural numbers. That's the point and the beauty of the Hindu Arabic system, right? It's a lot simpler than just working with strokes on a piece of bark. Much more efficient. And it allows us to deal with a lot bigger quantities. So if we have k digits available on a piece of bark, well, with natural numbers we can only get up to essentially k, but with these Hindu Arabic numerals we get up to essentially 10 to the k. So the possibilities for having arithmetic with bigger numbers is vastly expanded. Now, Arid Bishop's important dictum that meaningful distinctions need to be maintained needs to be kept in mind here as well. So we're using these Hindu Arabic numerals now in a number of different ways, and it's probably good for us to acknowledge these different ways that we're using them. So one way that we're using them is in an expression like this. We might write 34 is of type nat. And that means that this 34 is our Hindu Arabic shortcut for the primitive natural number given by this. Okay. So this is a primitive natural number consisting of a bunch of strokes, and we would express it as 1, 1, 1, 1, 1, etc. 34 times. But instead of writing this or saying 1, 1, 1, 1, 1, etc. 34 times, we'll allow ourselves to use our familiar Hindu Arabic number or numeral to represent this thing. And we'll talk about the natural number 34. Right? We do want to be able to talk about the natural number 34 and write something like this. So when we're expressing a primitive natural number by a Hindu Arabic expression, we're going to use this form. And this alerts us to the fact that we're actually thinking of a number of which is of type primitive natural number. As opposed to this usage where we have 34 as an element of num. Okay, so 34 being of type num is a shortcut for a base 10 vexil. So here this 34 is representing this base 10 vexil. So it's a vexil in the base 10 system. And I remind you that is really this thing here. Okay, so it's an M set of singletons with 3 zeros and 4 ones. So when we write 34 is of type num, we're really thinking in our minds that it represents this thing. When we represent or write down 34 is in nat, we're thinking that it represents this thing. There's a big difference. And let's also note that actually we can go one level down, because inside here, these things here are also natural numbers, but also in Hindu Arabic form. Right? And we could rewrite those just as primitive natural numbers. We can rewrite this 0 as this empty M set. And we can rewrite that 1 that's sitting there as the M set 1, which is the M set consisting of a single stroke. So if we're looking at 34 as a Hindu Arabic numeral, then ultimately it really comes down to this perhaps somewhat formidable looking expression. But that's sort of stripped of all higher level things, and we're going right down to the level of things involving emptiness and somethings. So it's emptiness or nothing and something packaged up and presented in a suitable data structure kind of way. And I think it's useful to just compare our orientation here with some basic programming structure. So in the programming world, there are various levels of programs. There are lower level programs and upper or higher level programs. And so here's a kind of a simplified view of that. So at the bottom, there's an actual machine that runs some hardware. And that machine typically is very simplistic at some level, maybe only dealing with zeros and ones ultimately. And then you have some machine language that's basically instructions that tells the computer what to do in terms of moving zeros and ones and changing them. And maybe then you have an assembly language, which is a little bit more sophisticated, but is another way of expressing or telling the machine what to do at the machine language level. And then there are these higher level languages where we have higher level constructs and things like C or Pascal or BASIC or COBOL, which ultimately sort of generate assembly language stuff and have to be compiled and assembled and so on to eventually get the machine to run. And then there's other, maybe even higher level languages, maybe Java, Python, MATLAB, things like that. Okay, so there's a kind of a level of hierarchy, of sophistication and of power. But ultimately, to actually run, you have to kind of go down and actually tell ultimately the machine what to actually do. So unless you have some logical stream that ultimately goes down here and is consistent and correct, then your program's not going to work very well. So analogous to that, we're doing something a little bit in the same direction here. We're thinking about having a system of numbers which are based on something that's very elementary and perhaps simplistic. Our basic dichotomy of nothing and something was, we said, sort of at the heart of things. That's sort of the essential building blocks. And from those things, we saw we could create natural numbers, or these primitive natural numbers. And that's just one step up from the sort of basic hardware, or this basic dichotomy of nothing and something. And now we've talked about these Hindu-Arabic numerals, or num. Okay, it's a little bit higher level. Okay, it's using the primitive natural numbers, but it's more sophisticated, more complicated, but also more powerful, more efficient in some ways. And we might also then want to go higher up, because we also want to think about expressions that evaluate to numbers. Right? So far we don't have any way of talking about 8 to the 7, or 17 factorial, or 4 triangle 5, or any of these higher hyper operations that we've been discussing. So this is then a natural kind of next realm to see, can we jack up our arithmetic with natural numbers from the level of Hindu-Arabic numerals to something more sophisticated, something more powerful, something that allows us to get at bigger and bigger numbers. Well, that's a very big challenge, actually. Okay, and I think it's fair to say that currently in modern mathematics we don't have a proper theory of these things. But we do want to talk about the challenges involved in setting up something like that and the kinds of choices that we might make. So that's what we'll do in our next video. We'll talk about the possibilities for creating a type in the direction of num expressions. We're looking for a way of working efficiently and consistently with arithmetical expressions that evaluate to numbers. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.